Good morning, everyone. Welcome to our new topic, physical equilibria. This topic will also be shared on our YouTube channel. In my YouTube channel, still I use the same names, Joseph Jobs Kaira. Please, you check in, subscribe for some other more videos there. So when you check and check those videos, don't forget to subscribe. Those who have subscribed, don't unsubscribe. All right. So yesterday, we had made an introduction about physical equilibria, and we said a physical equilibrium is an equilibrium that exists between different phases or physical properties. Okay, an equilibrium that exists between different phases or physical properties. And then you said it represents the existence of the same substance. Existence of the same substance, but in different physical states. And I remember emphasizing that physical equilibrium does not involve any chemical changes or any chemical reactions. Basically, physical changes, change in physical changes or solubility. Okay, I hope that was so clear. We defined the system yesterday, and we said that a system is that part of the universe and the energy associated, that part of the universe, the set of substances and energy associated with them that is being studied. And I remember giving you an example that when you have reactants in a physical, in a conical flask, when you put reactants in a conical flask, those reactants do react. When you put reactants in a conical flask, those reactants do react, and everything inside the flask will be a system. But if those substances do react within the conical flask, then that ceases to be a chemical equilibrium. It becomes a chemical reaction. So the substances in that flask must not react. They should only be undergoing physical or chemical, no, only physical changes or changes in solubility. So once a reaction takes place in the flask, then that ceases to be a physical equilibrium, becomes a chemical reaction. Okay. Nalima is out of class. I don't know what has happened. All right. So if the reactions are occurring in a conical flask, that's what I've been saying, that everything inside the conical flask is a system. But that shouldn't be reactions. We shall change this. It should be changes occurring within a conical flask. All right. We also defined a phase. Who can remind me what definition do we give for a phase? You all remember. Yes, we defined the system, a phase, and a component. If any of you does remember, how did we define a phase? Yes, Shamira.
A phase is a homogeneous part of a system which is physically distinct from other parts of the system by a definite boundary.
Okay, that's very correct. Excellent. You're saying that a phase is a homogeneous part of a system. And I told you what the word homogeneous means. A homogeneous part of the system which is physically distinct from other parts of the system by a definite boundary. Okay? The physical part of the system which is physically distinct from other parts of the system by a definite boundary. I remember giving you an example that if I have ice, water, and ice, liquid water, and what? And water vapor or steam. The three are different phases. We have the liquid phase, the gaseous phase, and the solid phase. Now, the liquid phase alone is always physically distinct, is always separated from other phases. You can easily know that when I look at the three, that this is the ice. This way it's separated from the other phases. So there is always a definite boundary that separates the phases in a system. Okay? And I told you they are normally or commonly three. They are commonly three. There are commonly three phases that are known: the solid, liquid, and gaseous phase. I gave you examples. I told you a mixture of gases is one phase. That's the gaseous phase. A solution is one phase. A saturated solution is a two-phase system, because we said in a saturated solution, there is both a solid, mixed with a solution. We have a solid mixed with a what? A solution. That's why we call it a saturated solution. Now the solid is one phase. The solution is another phase. You get it? And how do we form a saturated solution? We add a solid substance. For example, if I want to form a saturated solution of common salt, sodium chloride, I'll dissolve a lot of salt, sodium chloride, in water until no more salt can dissolve in that water. So until no more salt can dissolve in that water, that's when I've formed a saturated solution of sodium chloride. And that saturated solution forms what we call a two-phase system. Remember, sodium chloride does not react with water, it only ionizes. And that emphasizes what we call a physical equilibrium. Okay? Yeah, it's only substances that get mixed and go on changing in phases, but they do not react. They can only exist in equilibrium more than two phases. There are always two phases that can exist in equilibrium. But if you want more than two phases to coexist in equilibrium, then there are special conditions we must undertake. That's the purpose of this. We are saying except under special conditions, only two phases can exist in equilibrium. Okay? Are we together?
Yes, sir.
All right. Then we define the component as a pure substance in a system. Okay? We define the component as a pure substance in a system that it defines part of the composition of the system. And I remember telling you that a mixture of water has two components. This is where I want you to understand that when I have water and ethanol, both of these are what? Are liquids. Both of these are liquids. Okay? So both of these being liquids, that means there are two components but existing in one phase. If they are added together, they are two components. H2O is one component. H2O is one component mixed with another component, which is ethanol. Okay, so the two are two different components, but in one phase, which is the liquid phase. So that's what I want you to understand as a difference between a phase and a component. When you have ice and water are two phases. There is the solid phase and the liquid phase. So those are two phases, solid phase and liquid phase. But it's one component, H2O. Okay? So that's the difference you might have to understand between a phase and a component. If I'm to proceed, we talked about a phase diagram still yesterday, and we said this is a graph on which pressure is plotted against temperature. A graph on which pressure is plotted against temperature. Okay? A graph on which pressure is plotted against temperature. What does it show? It shows equilibria between different phases of a substance and the temperatures and pressures at which each phase exists. We are later going to see how a phase diagram looks like. I told you what each part on a phase diagram represents. An area or region on a phase diagram represents a phase, one phase. So if I want to show a liquid phase, I'll be using an area on the phase diagram. If I want to show the liquid phase, I'll use another area. If I want to show the solid phase, I will use another area. A liquid or curve on the phase diagram represents temperatures and pressures under which two phases can exist in equilibrium. A triple point represents the temperature and pressure under which three phases can coexist. Okay? Is this spelling correct, by the way? Remember, is this spelling correct for a triple point? Is that the word triple?
Yes.
Yes.
Yeah. You're lucky that you know it. Most people don't know that that spelling is like that. They write it as double P. So the word triple is a single P word. Triple point. In organic chemistry, if you're talking about the functional group in alkynes, which is the carbon-carbon triple bond, it is also a single P. So you should never write it as a word of this kind. Triple. This one is wrong. It is a word with a single P. I hope I can now proceed. This is where we stopped yesterday. That has been just a recap to remind you, those who are not around, what we looked at. Can I proceed?
Yes, teacher.
Okay.
Yes, teacher, you can proceed.
Now this is where we are. We are looking at component systems. We are looking at component systems. And somebody read for us this paragraph from here. Yes, to Musime.
There are two types of component systems, namely Roman one component system, only one pure chemical substance is involved in the equilibrium.
Yes.
Roman 2,
Mm.
two component system, two chemically independent components are involved in the equilibrium.
Very good. So if we talk about two component systems, they are basically two that we look at here. It is what we call a one component system. We define what a system as part of the universe and study. So if there is a one component system, in that one component system, there is only one pure substance. There is only one pure substance, chemical substance that is involved in the equilibrium. It only changes in phases. Okay, it may change from solid, it goes to liquid, it changes to gas, but it is the same substance, just like water does. Okay, just like water does. So water can have an equilibrium between its three physical states, between the solid and liquid, between the liquid and gas, between the gas and solid. But it still remains water, H2O. That's the pure chemical substance that is present in the system. Then there are two component systems, or a system that has two components. And in that system, there are always two chemically independent components involved. We shall see these ones later. But for now, we are going to begin with the one component system. That's what I want us to emphasize for now, the one component system. And that's what we are having here. Okay. Shamira, what are the three examples of one component systems as we shall look at this time?
Examples of one component systems include the water system, the sulfur system, and the carbon dioxide system.
So those are the three common one component systems that we shall look at advanced level. There is the water system, there is the sulfur system, and the carbon dioxide system. Now, this water system should not be a new system to us. You looked at it in senior one. You looked at the changes between the three different phases of water. Okay? You looked at those systems, the three different phases in which water exists. You looked at them in O level. At this level, we are just going to expound on them and see how equilibrium exists between the three. Is that clear? Can I proceed?
Yes, sir.
Okay. Here is the water system, our first system. You are all aware that water can exist as a liquid, it can exist as a solid, it can exist as a gas. Okay? Water can be a liquid, water can be a solid in form of ice, it can be water vapor. Okay? Now, some of you don't know the difference between water vapor and steam. You don't know the difference between water vapor and steam. When is water called water vapor? Water is called water vapor when the vapor is formed below 100 degrees Celsius. For example, when you wake up in the morning and move outside, maybe some of us have traveled in mornings to go through forests. When you go to a forest and try to observe above the trees, there is some moisture moving up on the tree canopy. That's what we call water vapor. Water vapor can exist even at the lowest temperatures possible. But when does water become steam? Water becomes steam if its temperature goes beyond 100 degrees Celsius after the boiling point. You get me?
Yes.
Teacher.
Yeah, so beyond the boiling point, water becomes steam. All right. Does anybody know somebody called Samuel or Sam?
No.
Samuel, good morning. Sam, good morning. Okay. So water is called steam when it's above 100 degrees Celsius. Let's carefully look at the phase diagram for water here. This is the phase diagram for water. This is the phase diagram for water. Who has given me color yellow? I hate this color. Let me pick another color here. Let me pick another color. Maybe this one, the pink one, will work better for me. So this is the water system. And here is what we call a phase diagram. Who can remind me? Or who can define for me what phase diagram for water is? What is a phase diagram for water? By definition. This is now a task to you. Who can define for me what's meant by the term phase diagram for water? Yes, Ali Tumusime.
Is a graph of plotted of pressure against temperature showing different phases of water.
That's a good trial. It's a plot of pressure against temperature showing equilibrium between the different phases of water. So now when you look at this, this is a plot of pressure against temperature. These are lines. What did we say about these lines? What does each line or each curve represent on this phase diagram? What did we say each line or each curve represents on this diagram?
It represents the pressure and temperature between over which different phases occur in equilibrium.
Yes. And then each area, for example, there is an area here, and this area is showing the solid phase of water. This area is showing the liquid phase of water. This area is showing the vapor phase of water. So that explains what we said, that each area on a phase diagram represents, each area on a phase diagram represents a given phase. Are we together?
Yes, teacher.
Yes.
All right. Now, if that's very clear, we can proceed. We are saying that at low temperatures and low pressures, water exists as ice. What do we mean by low temperatures and low pressures? At this point, we have low pressures, pressure below atmospheric pressure, then even low temperatures. In that area, water is existing as ice. Who can tell me why does water exist as ice at low temperature and low pressure? Why is water existing as ice at low temperature and low pressure? For example, who can tell me why? So nobody is trying. Yes, Ali.
Teacher, I think because of the components that make up, the molecules that make up water, when the pressures are low and the temperatures are very low, these molecules tend to be near each other.
Yes. they
More
tend to give so-
their kinetic energy is too low, meaning there is no movement of them, and then they exist into solid phase.
Very good explanation. I think you need a clap. Can somebody clap for Ali? Okay. Zoom has an option of clapping. Yeah, claps on reactions. So that's it. Water will exist as ice at low temperatures and low pressures. Then at low temperature and high pressure, that is this region here. See that region? Low temperature. Temperature is low, pressure is high. Water will exist as vapor. And then at high temperatures and high pressures, it exists as a liquid. So that's the difference between the phases. Okay. We need to know what each line here represents. We have this line or curve OA. Okay. We have this curve here, OA. This curve OA shows the variation in vapor pressure of ice with temperature. Can be asked what that curve shows. It shows the variation in vapor pressure of ice with temperature. Okay. So what happens as temperature increases, as pressure increases, the vapor pressure of ice increases. Ice is solid water. Are we together?
Yes, teacher.
Yes,
That
teacher.
line summarizes the conditions under which solid ice and water can exist. Solid ice and water vapor. These half arrows here show you that the ice, the solid water, is existing in equilibrium with the vapor, which is in this region here. So this curve shows variation in vapor pressure of ice, variation in vapor pressure of ice with the temperature. It summarizes the conditions or the temperatures and pressures under which solid ice and water vapor can be in equilibrium. The name of this curve is called the sublimation curve of ice. Why are we calling it the sublimation curve of ice? Because we are seeing that it is an equilibrium between solid and vapor water. Okay, water vapor and the solid water, which is ice. So the change from vapor to solid is sublimation. The change from solid to vapor is also sublimation. So that equilibrium shows sublimation. That's why we are calling it the sublimation curve of ice. Is that clear?
Yes, teacher.
Then OC, this curve here, OC, shows the variation in vapor pressure of liquid water with temperature. Okay, so always the state above the ice, the curve shows its variation in vapor pressure with the temperature. This shows variation in vapor pressure of solid water or ice with temperature. This one shows variation in vapor pressure of liquid water with temperature. Okay, it summarizes the conditions under which temperature and pressure, summarizes the conditions of temperature and pressure under which liquid water and vapor can exist in equilibrium. It's called the vaporization curve of liquid water. Okay, why do we call it the vaporization curve of liquid water? You see the equilibrium here. The equilibrium is between liquid water and the water vapor. Are we together?
Yes, teacher.
Then curve OB is this curve here. This one here is the curve OB. Okay. That curve shows the effect of pressure on the melting point of ice or freezing point of water. Okay, melting and freezing points are the same temperatures. So it shows the effect of pressure on the melting point of ice. Okay, why does it move this side? It means that as pressure increases, the melting point of ice decreases. You get me? That's why this line is slanting to the right. Okay, that as pressure increases, there is an increase in pressure. Instead of the line moving this way, it instead moves this side. What does that imply? It implies that as the it implies that we are saying that the line would be moving somewhere here. We shall see that later in the phase diagram for carbon dioxide. But instead of moving there, instead of moving in that direction, we are seeing that instead the curve is moving this side. Okay, why that way? The reason is because whenever pressure increases, pressure exerted on the water system, whenever it increases, the temperature or the melting point of ice decreases. In other words, the temperature is decreasing. So this curve OB shows the effect of pressure on the melting point of ice or freezing point of water. Okay, melting point of ice or freezing point of water. It shows equilibrium between ice and the liquid water. That curve can be called the freezing point, no, freezing curve of water or the fusion curve. That's the name we normally give it. Are we together, members?
Yes, teacher.
Can I
Yes, teacher.
proceed?
You can go on.
Okay. So here we are on the water system. We are continuing with the water system. I've just talked about this point here. I've just talked about this, that line OB slants upwards to the right, to the left. It slopes or slants upwards to the left because the melting point of ice decreases as the pressure increases. That's the reason. Then there are some points we need to name on that curve. Which points are those? We have point O. Point O is this point here. This point O is called the triple point of water. Is everybody able to see that point?
Yes, teacher.
Yes, teacher.
This point O here is called the triple point of water. We are going to see what a triple point is. Then this point C here, this point here is called the critical point of water. Okay, this is the triple point of water. That's the critical point of water. By definition, what are those points? What do you think is the definition for critical point? I mean triple point of water. Shamira, can you read for us this definition? Yes, Ali.
I read
Yes, what's the triple point?
the triple point refers to the particular temperature at which a particular pressure at which ice, water vapor, and liquid water can coexist at equilibrium.
Yes, the triple point refers to the particular temperature and the particular pressure, specify the two conditions, the particular temperature and the particular pressure at which ice, water vapor, and liquid water coexist at equilibrium. Okay, so triple point of water is the particular temperature and particular pressure at which ice, water vapor, and liquid water coexist at equilibrium. Then I think that's understandable. Then Ali, can you read for us what critical point is? I mean, should be Benjamin now.
Shall I begin?
Yes.
The critical point represents the particular temperature and particular pressure above which water vapor cannot condense to liquid water, no matter how much pressure is applied.
So this is somehow similar to the critical point of a given gas. If you remember, when you studied about the gaseous state of matter, you looked at the critical point of a gaseous phase, which was the temperature. Critical temperature of a gas is the temperature above which a gas cannot be liquefied no matter how much pressure is exerted on it. So when you talk about critical point of water, it is that particular temperature and the particular pressure above which, even if you go to heaven or to hell, water vapor will never condense to form liquid water, no matter how much pressure is exerted to it. You get me? Did you know that that
Yes.
point can exist? What is that temperature? At a temperature of 374 degrees Celsius, my friends, I tell you that whether you cook or crook, when water vapor reaches that temperature, 374 degrees Celsius, however much pressure will exert, that water vapor will never form liquid water again. Are we together? Is it that interesting? It's so much interesting. So the critical temperature, 374 degrees Celsius, is the temperature above which water vapor cannot be converted into liquid water, no matter how much pressure is exerted. And beyond that temperature, liquid water and water vapor are undistinguishable. Members, can I proceed?
Yes.
Yes, sir.
Okay. Here we are with some questions. We are looking at the effect of temperature and pressure on the different phases. Effect of temperature and pressure on the different phases. So I still have the water system being drawn here. And I have some questions I want to ask. These are the questions which I want you to answer. The diagram above is a phase diagram for the water system. Name regions A, B, and C. Name regions A, B, and C. Yes, Shamira, which region is region A?
It is solid. Solid region.
You You see now how we fail. We don't call it the solid region. We neither call it the solid. You can tell me which name shall we give it? If you're naming it. Yes, Ali.
It is
Yes?
solid phase.
Yes, we shall call it the solid phase. Then region B, same under what is region B?
It is a liquid phase.
The liquid phase. And then that means region C is obviously Ian. Ian, what is region
The-
C?
Vapor phase.
Yes,
It is the vapor phase.
the vapor phase. That's very correct. Yes, Benjamin, what is point Q? Benjamin is still around. Ali, what is point Q?
Triple point.
And then what is point Z, Shamira?
Critical point.
A critical point. Very good. Name the curves QY. What is curve QY? Shamira. What is curve QY, Shamira?
The vaporization curve.
So this state here is solid, and this is liquid. So solid to liquid, that's vaporization. That's correct. Then, yes, Frederick. So what tells you is the phase?
freezing curve.
This is a solid.
It is solid and liquid. It is a freezing curve.
This is equilibrium between a solid, and here we have liquid phase. So equilibrium between a solid and a liquid is which equilibrium? That is fusion or freezing, not so. Therefore, this curve here is called the fusion curve or the freezing curve. Are we together?
Curve.
Yes, thank you.
Then what is curve 2x? Yes, Amanda.
It is a sublimation curve.
It is the sublimation curve. And lastly, what is curve 2w?
It is a vaporization curve.
That is the vaporization curve. Shows equilibrium between the liquid temperatures and pressures, and at which liquid and vapor are in equilibrium. Then who can state why curve 2y slants to the left? Which reason did we give for that? Why does curve 2y slant to the left? Shamita.
QY slant to the left because the melting point of ice decreases as pressure increases.
Very correct. The melting point of ice decreases as pressure is increased. Now, this is the most interesting part I want us to emphasize now here. The first were preliminary questions that I thought everyone could be able to answer. Okay. You can be asked to explain the changes that take place when the temperature of the system is increased from F to G at a constant pressure. Are we there now, members?
Yes, sir.
Yes, sir.
Yes, we want to explain what happens when the temperature of the system is increased from F to G. I think I need to clear my diagram here so that you can be able to see what I mean. So this is F. Okay. This is F, and this is point F, and this is point G. From F to G, it is temperature being increased. Did you realize that? Temperature is increasing, okay? But the pressure is remaining constant at this pressure here. So the pressure is remaining constant to the value here, but the temperature is going on increasing. Now they want us to explain the changes that do take place. This is not so hard. It's very easy. What you do, actually, they sometimes give you temperature values. They can give you the temperature value here. Instead of if they give you the temperature here, then they also give you the temperature here. They give you the two temperatures instead of F and G. They can tell you to explain if this temperature is maybe 20, and this temperature is maybe 300 or maybe 200. They tell you to explain the changes that take place when the temperature is increased from 20 degrees Celsius to 200 degrees Celsius at a constant pressure. Okay, so for you, what you do, you label this point F in this region, you label this point G, and after labeling those points, you draw a dotted line there to guide you. You label these points that are where your line meets the curves or the lines. For me, I labeled this as H and this as P. Are we together?
Yes, sir.
And after doing that,
Yes, sir.
you start your explanation. We must know this phase here. In this region, what exists in which phase? It exists as a
Ice.
solid, right?
Solid phase.
Then in this region, what is existing as?
Liquid phase.
Liquid.
Liquid. Then in this region, what is existing as?
Vapor.
Vapor. Now, after knowing that, that's going to guide you as you're explaining. What will you say? Can we mute ourselves to avoid the interference? So we shall say at F, that's the first thing you tell us. At point F, what exists in the solid phase? That gives you half a mark. Okay? You tell us what exists at point F. At point F, what exists in the solid phase. Then you tell us what happens when you increase temperature. Increase in temperature of ice moves the system from F to H, okay, without changing phase. That statement gives you half a mark. So tell us that increase in temperature of ice moves the system from F to H without changing phase. Are we together?
Yes, teacher.
Why are we saying without changing phase? Because this is still the solid phase. Then what happens at H? Tell us what happens at each point and along each line. So at H, the ice now begins to melt because it's going to change to a liquid. You get me?
Yes.
So the ice begins to melt and the temperature remains constant until all the ice has melted or until all the ice is molten. Are we together?
Yes.
So at H, ice begins to melt and the temperature remains constant. Why? During melting, temperature is always constant, so that one must be emphasized. If it's not emphasized, you don't get that mark, okay? So at H, ice begins to melt and the temperature remains constant until all the ice has melted. Then what happens? After all the ice has melted, further increase in temperature will move the system from H to P in the liquid phase. That's what this statement is saying, okay? When you increase the temperature further, after all the ice has melted, when you increase the temperature further, remember you are moving inside, you're increasing the temperature. The system will move from H to P in the liquid phase. Who can tell me what happens at point P?
No temperature changes.
That's not what you write. You'll say temperature remains constant, but you want to know what happens there. Yes, Shamila.
Water begins to vaporize.
So we are saying that at point P now, the liquid water begins to vaporize. So the liquid water begins to vaporize and the temperature remains constant until all the water has vaporized. Remember, it was now liquid. So at this point, it begins to vaporize and the temperature remains constant until all the water has done what? Until all the water has vaporized. Okay? You get the point, members. So at point P, liquid water begins to vaporize and temperature remains constant until all the water has vaporized. So after point P, what happens? Further increase in temperature moves the system from P to G in the vapor phase. So you have to explain it as simple as that. Are we together?
Yes, teacher.
Yes, teacher.
Now, if that is very clear, I'm also going to give you a question because you seem to have understood this. The question I'm going to give you is this. Can you listen to my question? The question says, explain the changes that take place if the temperature of the system is decreased from D to F at constant pressure. I want somebody to explain for me that. Explain the changes that take place when the temperature of the system is decreased from D to F at a constant pressure.
Pardon the question, teacher.
The question is the reverse of this one. Explain the changes that take place when the temperature of the system is decreased from G to F. From G to F, we are decreasing the temperature at a constant pressure. I want somebody to explain that. Yes, Ali.
At G, water exists in vapor phase.
Very good. Mhm.
A decrease in pressure of vapor.
Why are you talking of pressure now? We said the pressure is constant, right?
Yes, teacher.
Yes, the pressure is constant. So
I
can't
pardon
increase
myself.
pressure.
A decrease in temperature of vapor moves the system from G to P without change in phase.
Very good.
At P, vapor begins to liquefy.
Yes, you can say the vapor begins to liquefy or the vapor begins to condense. Mhm.
The vapor begins to condense and the temperature remains constant until until the vapor has liquefied.
Yes, until all the vapor has liquefied or condensed. Very good. Mhm.
After the liquid has been formed, further increase.
You say after all the vapor has liquefied.
After all the vapor has liquefied, further decrease in temperature will move the system from P to H in the liquid phase.
Very good.
At H, liquid water begins to solidify.
Yes, you can say liquid water begins to solidify or liquid water begins to freeze.
And the temperature remains constant until all the water has solidified.
Very good.
Further decrease in temperature moves the system from H to F in the solid phase.
Very, very, very good. That's excellent. Let me hope everybody could give it that way. So when you talk about these points, P and H, at those points, you must emphasize the point that temperature remains constant. Can I proceed, members? Has that been clear?
Yes, sir.
So if that's very fine, we can now proceed to the next question. Next question says, we are still explaining the changes that take place when pressure of the system is reduced from J to K. J is here. We are reducing the pressure now. This is pressure reducing. We are moving downwards. We are reducing the pressure from J to K at a constant temperature. So when we reduce pressure, the temperature is maintained constant. When we increase the temperature, then the pressure is kept constant. That's the idea here. Still settling something here that is a bit disturbing. So here we are. We are explaining the changes that take place when the pressure of the system is reduced from, we are reducing the pressure from J to K at constant temperature. Are we together? So we shall begin by saying this is J. What happens at J? At J, water exists in the liquid phase. Okay. Then we go ahead and say reducing the pressure of liquid water moves the system from J to H without changing phase. Here I'm very quick because you've got the concept at first. Then at H, what happens? The liquid water begins to freeze because now changing to the solid. This is liquid now to solid. So the liquid water begins to freeze. Now here what remains constant is the pressure. I want you to note this. Here what is remaining constant is the pressure, not the temperature. Okay? So the pressure remains constant until all the water has frozen. Are we together? Because we are changing pressure. Here we are changing temperature, that's why we say this temperature remaining constant. Here we are changing pressure, that's why we are saying pressure is remaining constant. So the liquid water begins to freeze and the pressure remains constant until all the water has frozen. Now, after all the liquid water has frozen, a further decrease in pressure will move the system from H to M. This is point M. That is in the solid phase. You get it? Then at point M, what happens? Solid water begins to sublime or to vaporize. So ice begins to sublime at this point, changing it to vapor. And the pressure remains constant until all the ice has sublimed. Are we together?
Yes, teacher.
Then a further decrease in pressure will move the system from M to K in the vapor phase. Is that very clear, members?
Yes, teacher.
All right, if that's very clear, then I want somebody to explain it to me. What happens when the pressure of the system is increased from K to J at a constant temperature? I want somebody else other than Ali now. what will happen? Somebody's explaining what will happen if the pressure of the system is increased from K to J at a constant temperature. This time I want somebody else other than Ali. Yes, Shamira.
Okay. Okay, what exists in vapor phase?
Yes.
Increase in vapor pressure. Increase in vapor pressure. Excuse me, master. Exists in vapor phase.
As if I'm not hearing you, Shamira. What's the problem? Shamira, I'm not hearing you. You begin from where you started from.
Okay. Water exists in vapor phase.
Yes, you are now clear.
Increasing the pressure of the liquid moves the liquid to the solid, to the
doesn't
moves
move
the
the liquid,
moves to
moves
the
system.
to the solid phase.
No, it moves the system from K to M.
From K to M.
In the
at M, in the system.
This is how you begin. We said at K, water exists as a vapor, right? Are you getting me, Shamira? So increase in pressure moves the system from K to M in the vapor phase. Then you tell us what happens at M.
At M, the begins to solidify the vapor.
Yes, the vapor begins to solidify. That's correct.
And the pressure remains constant until the water is frozen.
Yes, until the vapor is frozen. Good.
Further increase moves the system.
Further increase in what?
Further increase in pressure moves the system from M to H.
Yes, in the solid phase.
Yes. At H, at H, the solid begins to liquefy.
Yes, you can say the solid begin, but I hate the word liquefy because most of you don't know how to write that word. The word liquefy is written like this. Liquefy. Now, some of you don't know how to write it, and instead you write, this is the correct word. Some of you write it like this, liquefy, which is wrong. So I prefer you using the word, maybe here you can say that at point H, ice, over solid water, ice begins to melt, it's changing from solid to liquid. If you can remember the correct spelling, the better. So you go ahead.
At H, the solid begins to condense, to liquefy. Point H, further increase in pressure moves the
There's
system
something
to
you've not mentioned here. At H, ice begins to melt. So you must tell us that pressure, it's now pressure remaining constant until all the ice is molten. Are we together? Are we together, Shamira? Yes. Now you tell me what happens along HJ. At HJ.
further increase in pressure moves the system from H to J.
That's very correct. Yes, you've struggled, but at least I know you've understood how to approach that.
Yes, sir.
Okay, has everybody understood that? Can I proceed? Yes, Ali.
Teacher, there is something I'm asking about. For example, description we have on number 2, but it is the same case with number 1. I just want to understand. When we are talking, for example, we say reducing the pressure of the liquid water moves the system from J to H, but we don't state where the pressure, how much have we reduced. I just think maybe we also need to tell that the pressure from this to this.
Now here the pressure values are not given, right?
Yes.
So you don't have to specify them unless they are given.
Oh.
Yes. Just use letters.
So let us talk about only system. They don't talk about pressure.
Yes. Use J to H. Unless the pressure values are given on this axis, then you quote them as you are giving them here. But even if you don't quote them and use these letters, somebody still understand that. You can't be penalized for that.
Okay, teacher.
So can I proceed?
Yes.
So here we are to another system. And this is the carbon dioxide system. This is the system we shall end with today. Okay. We are saying that like water, carbon dioxide can also exist as a liquid, solid, or gas. I think at your level you heard about solid carbon dioxide. Did you?
Yes, teacher, we heard of.
Yeah, solid carbon dioxide, and you heard that it's one of the substances that sublime. So just like water, solid carbon dioxide, carbon dioxide can also exist as a solid, a liquid, or gas, and its phase diagram is not so different from that of water. Maybe it differs only in one thing. Who can tell me which one thing distinguishes the phase diagram for carbon dioxide from that of water? What do you think distinguishes the phase diagram of carbon dioxide from that of water? Who can really tell me the difference between the two? Yes, Ali.
When we look at carbon dioxide system, the carbon dioxide has the triple point is higher than that of water.
Okay, that's right. But I wanted the difference to be in terms of these curves, the three curves. What do you notice?
I noticed that PR curve slants rightwards as pressure increases.
Very good. That's the main difference. This curve here, which we call the fusion curve or the freezing curve, for carbon dioxide, it slants upwards to the right. And then for the water system, it was slanting upwards to the left. Have you got that, Shamira? Frederick, have you understood that difference?
Yes, sir.
Yeah, that's what we shall explain later. Why is it like that? Okay. Now, just like water, this phase is a solid phase for solid carbon dioxide. This is a phase for liquid carbon dioxide. This is a phase for gaseous carbon dioxide. Okay, P is the triple point of carbon dioxide now. Must specify which substance. S, just like water, is the triple point for carbon dioxide. Okay. When we look at the curves, it should not confuse you. They are the same curves we have been naming. PQ, this curve here, shows equilibrium between solid and gas. That's the sublimation curve of solid carbon dioxide. Okay. Sublimation curve of solid carbon dioxide shows vaporization, vapor pressure of solid carbon dioxide with the temperature. If they ask you what it shows, then PS is the vaporization curve of liquid carbon dioxide. Okay, vaporization curve of liquid carbon dioxide. Yes, that's the vaporization curve of liquid carbon dioxide. Okay. And then curve PS is the freezing curve of fusion curve. What does it represent? Shows the effect of pressure on the melting point of solid carbon dioxide or freezing point of liquid carbon dioxide. So this is what I've been talking about. The triple point of carbon dioxide is specified as negative 56.4 degrees Celsius and 517.5 kilopascals, or when you convert it to pascals, it's 517500 pascals. So what does that imply? At this temperature is so low and this pressure is so high. That means that liquid carbon dioxide cannot exist at ordinary temperature and pressure. I think there is nothing much here, members. You clearly understand this. It's not different from that of the phase diagram for water, apart from the slanting way of the fusion curve. Are we together?
Yes.
Yes, sir.
All right. And now we may proceed to the next what? To the next question. Are we here? Yes, here we are. Now here we are naming regions A, B, and C. Who is answering Roman 1? This phase diagram. By the way, you can be given this phase diagram and they ask you which substance is represented by the phase diagram. You can only know by this curve here. It can tell you whether the phase diagram is for water or for carbon dioxide. So sometimes you can be given and they tell you to name the substance responsible for this phase diagram. So you can name regions A, B, and C. Yes, Shamira.
Is the solid phase.
Mhm.
Is the solid phase. Phase B is the solid phase. Phase B is the liquid phase, and is the gaseous phase.
Okay. Any points O and Y?
Actually, you can answer.
Yes, please.
Point 4 is the triple point, and point Y is the critical point.
O is the triple point of carbon dioxide. Y is the critical point of carbon dioxide. Okay. Who can name curve OQ, OR, and OY? What is curve? I mean OX. What's curve OX?
OX is a freezing curve. OR
Freezing curve
is a
of what?
sublimation
Must
curve.
specify.
Okay. OX is a freezing curve of carbon dioxide.
You've not
OR
specified.
is
Not specified. You've not specified. Yes, Ali, can you specify what curve OX is? Members, I want you to go back here and note this. We said this is solid carbon dioxide and this is liquid carbon dioxide. Okay. Now this curve here is a sublimation curve of solid carbon dioxide. There is need to specify these states here. Then PS is vaporization curve of liquid carbon dioxide. This is liquid carbon dioxide vaporizing, turning into gas. So we must specify which state is changing. It's only the freezing curve where we don't specify. The PR here we don't specify. But these two curves, PQ and PS, we must specify. So again, come back here. What is curve OX? That is a fusion curve. Are we together? So for that one, don't have to specify. What is curve OR? Let's continue with that. What's curve OR? Yes, Ali.
Curve OR is the sublimation curve of carbon dioxide.
Of solid carbon dioxide. Is that clear?
Yes, yes, teacher.
Curve OY. Who's naming curve OY?
Curve OY is vaporization curve of liquid carbon dioxide.
Very good. Vaporization curve of liquid carbon dioxide. Ian, are you following?
Yes, sir.
Ian, why does line OX slope to the right?
It stops the rate because melting point of solid carbon dioxide increases with pressure, with increase in pressure.
Very good. The melting point of solid carbon dioxide increases with increase in pressure. Now we come to these changes. We explain these changes that take place. Explain the changes that take place when pressure of the system is decreased. We are decreasing pressure from D to E at a constant temperature. Yes, Benjamin.
Previously, I was disrupted when we are explaining because I was in the noisy place. So I would like you to repeat, pardon for me, on how we name the curves, how we know that this one is the sublimation curve of solid carbon dioxide, how we know that it is the freezing curve, the vaporization curve, all those.
You're giving me hard work now.
Yes, I didn't get the point because even I wasn't following because I was disrupted. I was in the noisy place.
Now, we said this is a phase for solid carbon dioxide. This is a phase for gaseous carbon dioxide. And this phase here is the liquid. So you can easily know that equilibrium between a solid and vapor is sublimation. You get that? You get that, Benjamin?
Yes.
Equilibrium between a solid and vapor is sublimation. So this is a sublimation curve of solid carbon dioxide. You get that?
Okay, yeah, I'm getting.
This is equilibrium between a liquid and a solid. So what change occurs between a solid and a liquid? Which change is that? Benjamin, are you there?
Yes, I'm there.
What change occurs between a solid and a liquid?
It is melting.
So which curve is this?
The melting curve of solid carbon dioxide.
So if I'm to take you back, this curve here, PR, is the freezing curve. Okay? It is freezing curve. The liquid changes to solid by freezing. That's why we call it the freezing curve or the fusion curve. Then this curve here is showing equilibrium between a liquid and a vapor. So equilibrium between liquid and vapor is normally, you know that vapor changes into liquid by condensation, or liquid changes into vapor by vaporization. So this becomes a vaporization curve. I think it's now clear to you.
Yeah, I'm picking.
Okay. Now, after you've understood that, we are explaining the changes in the pressure. The changes that take place when pressure is decreased from D to E. This is point D. This is point E at constant temperature. So at D, carbon dioxide is a solid. That's the first thing we need to know. At this point, carbon dioxide is a solid in the solid state. Then decrease in pressure of solid carbon dioxide moves the system from D to H without changing phase. At H, solid carbon dioxide begins to melt or to liquefy, and the pressure remains constant until all the solid carbon dioxide is molten. Are we together? Now, after all the solid carbon dioxide is molten, further decrease in pressure will move the system from H to J in the liquid phase. Okay? Then at J, liquid carbon dioxide begins to vaporize because this is now a gas. It begins to change to gas. So liquid carbon dioxide begins to vaporize and the pressure remains constant until the liquid carbon dioxide has vaporized. So further decrease in pressure moves the system from J to E in the vapor phase. I think that's very clear. Normally, if you understood that for water, this doesn't confuse you at any little bit. Are we together?
Yes, sir.
Now we're explaining what happens when temperature of the system is increased from F to G. We're increasing temperature of the system from F to G. This is F to G at a constant pressure. So this is already understood that at F, carbon dioxide is a solid. So increasing the temperature of solid carbon dioxide will move the system from F to K without changing in the solid phase. At K, solid carbon dioxide begins to liquefy, or solid carbon dioxide begins to melt, and temperature remains constant until the solid carbon dioxide is molten. Okay. Now, after all the solid carbon dioxide is molten, a further increase in temperature will move the system from K to L in the liquid phase. At L, liquid carbon dioxide begins to vaporize and temperature remains constant until all the liquid carbon dioxide has vaporized. Further increase in temperature will move the system from L to G in the gaseous phase. Are we together, members?
Yes, teacher.
Yes. Now today, we have redefined the system, a phase and a component. We have looked at the water system, the different phases and the effect of temperature and pressure on the phases. We have looked at the carbon dioxide system. It's difference between the difference between the water system and the carbon dioxide system, and the effect of temperature and pressure on the carbon dioxide system. The next time we meet, we shall be looking extensively at the sulfur system, and we shall proceed. This is where I would wish to end today's lesson. But Ali Tumusime has his hand up. What's your issue, Ali?
Teacher, I would like you to explain to me if these two things are different from each other and how. Vapor from a gas, over vapor and gas, how are they different? Another question I just have too. When we look at this graph, we look at the solid phase and the liquid phase by being separated by the OX curve. Yes, teacher?
Yes, please.
If someone wants to tell this curve differently from what we have been saying, for example, we see there is a process which changes from a solid to a liquid, and there is another process which can change a liquid to a solid. If those two things, is it the same answer or a different answer? And if they are different, right?
Now, normally we use the word vapor when we are referring to water. Okay, that's why I was using it in the water system, right?
Yes, teacher.
With carbon dioxide, I'm calling it a gas. is gaseous carbon dioxide instead of vapor. Then the second thing is that this curve here is always called the fusion curve. Because we look at a liquid, we could call it the melting curve of solid carbon dioxide. That would also be fine, but it is better you call it the fusion curve of liquid carbon dioxide, or simply the fusion curve. That would be better. Are we together?
Then teacher, I'm getting you and I'm getting you. Now on this one, backing to is evaporization curve, yet there is no water here.
I'm not getting you, Ali. What are you saying?
Teacher, I'm saying, you said we only use vapor when we are referring to water. But when we were answering these curves, OY curve, we named it as evaporization curve. Were we right or wrong?
We are right. However much the word vapor is basically used for water, there is no other term we can use here. We cannot say this is, for example, change from liquid to gas is taken as vaporization. Although this is carbon dioxide, there couldn't be no any other term we can use. But if you are referring to carbon dioxide alone, you cannot say vapor carbon dioxide. The best thing we can call it is gaseous carbon dioxide.
Thanks,
Thank
teacher,
you
so
for
much.
attending the lesson. Go to the YouTube channel, subscribe for more videos. We meet next time. Thank you and have a good day.
Okay.
Likewise.
Thank you, sir.